All right, guys, here we are again. Video number 3 of the peripheral nervous system. So this one is going to get us a little bit deeper into the synapse and the neurotransmitters. So we're going to just review normal synapse function. We're going to talk about the two main transmitters of the autonomic nervous system, which are norepinephrine and acetylcholine. And then we're going to talk about how we stimulate and how we terminate the action at our primary receptors of the autonomic nervous system, which are going to be the adrenergic receptors, the alphas and the betas, and the cholinergic receptors, the muscarinic receptors, and the nicotinic receptors. So that's the game plan for this next little bit. So as you guys know, the functional cell, or the functional cell of the nervous system, is the neuron. Neurons are kind of cool cells. They're very specialized because they have the ability to receive and relay, I should say, impulses. So they have these long processes that hang off of them. They have a cell body like all cells with a nucleus and all the other stuff you find in cells. But they have these sort of finger-like projections that are going to bring information towards the cell body, and those are called dendrites. And then they have that long sort of tail-like structure that stretches away from the cell body, and that is called an axon. At the end of the axon, that's where all the magic happens in the autonomic nervous system, because that's where the neurotransmitters, acetylcholine and norepinephrine, are going to be released from. And then they are going to stimulate a receptor that's on some sort of downstream location, whether it be another neuron, in this case would be the postganglionic neuron, or the target. All right, so these neurons are the cells, special cells of the nervous system that are able to conduct these electrical kinds of impulses. There's a picture of some real neurons. They're kind of cool looking cells. Okay, so diving into this, when we have one neuron ending and something else starting, whether it be another neuron or whether it be a target, an effector, the space, so if we were to draw a big circle around this, that would be a synapse. So the synapse is essentially the meeting of two neurons. To get a little more specific, if we were just talking about that little itty-bitty space between the terminal portion of one axon and the target or the beginning of the postganglionic neuron, that tiny little space in between, which would be here and here, that's called the synaptic cleft. So the synaptic cleft is more specific, and that's where we're going to be focusing our attention, because these little circles here are called vesicles, and they're holding neurotransmitters right there. They house neurotransmitters, and they're going to get spit into the synaptic cleft, and then they're going to bind a downstream receptor. Sorry for the sound effects. My ridiculously large dog is thirsty. Okay, so let's think about a synapse for a second. So there's steps when we talk about, the steps of what's going on at the synapse. So the first thing that has to happen is, first we have to synthesize a neurotransmitter, right? So the neurotransmitters are going to be made either by the cell body or they're made in the terminal portion of the axon. The neurotransmitters that we're talking about here are norepinephrine and acetylcholine. All right, so they're made and they're kind of stuck into these vesicles, or they're stored in these vesicles, right? The thing about this is neurons travel super fast, right? They have to travel really fast, and there has to be enough neurotransmitter there for us to be able to A, relay the message, but B, to be able to have them stimulated again when the next message comes, right? So there's got to be a pretty ample supply of neurotransmitter available. And how we have enough neurotransmitter available is it gets made and then it gets packaged in these little vesicles and it just hangs out there. There's any number of, I think if I remember, I thought I wrote it down, but there's something like, for acetylcholine, something like 30,000 vesicles, each with 5,000 molecules of acetylcholine or some ridiculously large number of neurotransmitter sitting in the terminal portion of the axon. So there's a lot of neurotransmitter available, right? We don't really run, under normal conditions, we're not going to run out. Okay, so first we synthesize it, then we store it in a vesicle. And then what has to happen is that transmitter substance, or that neurotransmitter, has to be released. All right, so what's going to end up happening is that an action potential is going to arrive at the terminal portion of the axon, and that's going to stimulate. And there's sort of a lot of steps you probably remember from physiology, like calcium channels open and calcium rushes in, and that causes the release of the vesicle. So the vesicle kind of goes down and it fuses. It's membrane bound, so it fuses with the cell membrane of the neuron at the axon terminal, and it gets spit out into the synaptic cleft via exocytosis. So the neurotransmitter is released into the synaptic cleft, and then it's going to float down and it's going to bind a downstream receptor. Right, so when it binds a downstream receptor, that receptor is on a postsynaptic cell or a target. Remember, we can have this happening at the ganglia between two neurons, or we could be happening between the postganglionic neuron and the target. Either way, right? Same situation happens. So the neurotransmitter binds a receptor on the downstream thing, whether it's a postganglionic neuron or whether it's the effector, and then that's what stimulates the action, right? That's going to cause the characteristic action, whether it be a sympathetic response, a parasympathetic response, or the type of response that we see at a ganglia, which we'll get into more in a little bit. But after that happens, then we got to get rid of that neurotransmitter, right? So the deal is it binds quickly and then it gets kicked off, right? It's transient, it's fast, it comes on, it's off, it's done, and then we need to get rid of it. And so what we do is then we destroy it either by an enzyme in the synaptic cleft, which is how acetylcholine gets destroyed, or sometimes it gets recycled. That neurotransmitter gets recycled. It gets sucked back into the neuron that released it. That's called a reuptake mechanism. And then an enzyme will be in the preganglionic neuron in this case, and that will kind of take it apart. So enzymatic destruction happens in either case. It's faster with acetylcholine and slower with norepinephrine, because with acetylcholine, there's an enzyme right there in the synaptic cleft, which we'll talk about. I'll show you a picture of in a second. That just breaks it down. It's probably on the next slide. But the purpose of removing the neurotransmitter is it allows for this whole situation to kind of get reset, and it allows for continuous stimulation, right? So it allows for synapse function to continue. And it also controls the response, right? You wouldn't want this neurotransmitter to be there and keep hitting and hitting and hitting. It's a more graded response that way. Okay, so here's the picture that I was referring to. This picture deals with a preganglionic and a postganglionic neuron, as you can see. So this preganglionic neuron is going to release acetylcholine, and you can see here it's illustrated. It would be in vesicles. We can't see that, but that's okay. Just imagine that's in a bubble. And this vesicle is going to come down here, and it's going to fuse with this membrane, and it's going to spit these little green triangles, which are illustrating acetylcholine, into the synaptic cleft. And then down here on this neuron, right, this is another neuron, that you have a receptor for acetylcholine specific. So it binds this receptor. And then what's going to happen is it's going to get kicked off, and it's going to get broken down by an enzyme. That enzyme is called acetylcholine esterase. You can see it down here. Acetylcholine esterase is going to very quickly degrade that neurotransmitter and stop the response. And then what's going to happen is the bits and pieces are going to essentially get recycled and rebuild, and they'll be used to rebuild acetylcholine, right? At least part of it. The choline part, and then the rest of the acetylcholine comes from acetyl-CoA, which is the first step, if you recall, in the Krebs cycle. Anyway, that's how it's made, that's how it's released, that's how it binds the receptor, and that's how the action is terminated. That kind of response happens whenever we have a neurotransmitter being released. This is all about synaptic transmission. This is how it goes down. It doesn't matter if it's acetylcholine, it doesn't matter if it's norepinephrine, it doesn't matter if it's epinephrine, it doesn't matter if it's dopamine, glutamate, glutamine, etc. It works that way. GABA, it works that way across the board. So that we got to understand. Here's a cool picture, another scanning electron microscope of vesicles, right? This would be the vesicles being released essentially into the synaptic cleft. That's a cool picture. All right, so we're going to look at the two different synapses. So we are dealing with two neurotransmitters that we're talking about. There are more, but we're talking about two because these are the primary neurotransmitters of the autonomic nervous system. So what we have here is what we call an adrenergic synapse. So we're going to become very familiar with the two terms adrenergic and cholinergic. A neuron that releases norepinephrine is referred to as an adrenergic neuron. And the reason for that is because norepinephrine used to be called adrenaline, and adrenergic comes from adrenaline. But there's some sort of a long story on why. I think we are the only ones, this country is the only one that refers to norepinephrine as norepinephrine. Everybody else, I believe, still calls it adrenaline. And some of us still call it adrenaline also. But that's the story. So that's where the term adrenergic came from. So you can see here that norepinephrine ultimately is made from, starting at the top, tyrosine gets converted to, gets converted to dopa, which gets converted to dopamine, which then gets converted to norepinephrine. That gets stuffed in the vesicles, and that waits around for the action potential. The action potential arrives. You can see that happening here. That causes a calcium influx, which essentially causes the vesicles to be released. They come down here, they fuse with this membrane, and they spit that norepinephrine out into the synapse, into the synaptic cleft, I should say. These little cute green guys are receptors for norepinephrine, so we'd call those adrenergic receptors. And we're going to get more detailed later. So an adrenergic neuron releases norepinephrine as the neurotransmitter. That norepinephrine is going to bind an adrenergic receptor on the downstream neuron, or, at the case of a target, the target. Then that norepinephrine's got to get out of there. We don't want to keep it there, so we got to get it out of there. And so norepinephrine gets sucked back up by what we refer to as a reuptake mechanism. And you can see that happening. Sorry, I have something in front of my screen. So this reuptake mechanism, we have one happening here, getting recycled back into the presynaptic neuron and then getting degraded by an enzyme called monoamine oxidase, MAO enzyme. The other option is for norepinephrine to get kind of sucked down here into the postganglionic neuron, in this case. And there's another enzyme called COMT, C-O-M-T, which is catecholamine methyltransferase, I believe. And that guy is going to also get norepi out of the synapse. But what I want you to remember is norepinephrine is removed from the synapse by a reuptake mechanism, and it tends to be slower. The removal process is slower with norepi than it is with acetylcholine. That's what I want you to remember. And the reason why we want to get it out of there is we don't want to keep stimulating these receptors, right? This is a transient effect. You get an action potential, the neurotransmitters are released, and then they get out of there. They're removed, right? And then we wait for the whole thing to happen again. The same kind of a setup with the cholinergic synapse. So the cholinergic synapse, so this is like the one we saw before. This is a cholinergic neuron. All cholinergic neurons release acetylcholine as their neurotransmitter. All right, acetylcholine is going to be housed in these little vesicles, like I said. Arrival of the action potential, the same kind of action potential, it's just an electrical signal, right? It gets down here. When it gets to the terminal portion of the axon, that triggers the opening of calcium channels. Calcium comes in, causing the vesicles to move down, fuse with this membrane, spit the acetylcholine out. This is a nice, we got it all blown up here. Spit acetylcholine out, and then we have these receptors for acetylcholine right here. And then, so the acetylcholine hits the receptor, gets bounced off the receptor, and right here in the synapse, you've got acetylcholine esterase. That's an enzyme's job to cleave that acetylcholine into bits, right? The choline gets recycled, the acetyl leaves, and then we rebuild it with acetyl-CoA and choline to make more acetylcholine in the preganglionic neuron. All right, so this one's fast. This is faster. It's because the enzymes are right there. It hits, bounces off, cleave it. That's the way it works. Pardon me. Here's another picture showing the same thing. Right, this is two neurons coming together, preganglionic in red, postganglionic in yellow. Here's our little itty bitty space between, there's our synapse. Blow it way up here, right? So we've got the vesicle housing our neurotransmitter. In this case, it's acetylcholine, so that would be a, what kind of neuron? Cholinergic. It's a cholinergic neuron, right? That's neurotransmitter gets released into the synaptic cleft. It's going to then float across, right? We're going to flood the synaptic cleft with acetylcholine. It's going to fit into that cute little receptor right there, which is a cholinergic receptor. It's one of the two types of cholinergic receptors, which is called a nicotinic receptor. And then it's going to get bounced off, and it's going to get cleaved by acetylcholinesterase and get out of there and get removed, right? There it is. So the beauty of this system is it allows for one-way transmission, right? Acetylcholine can only produce an action when it binds a receptor. You notice over here, there are no receptors for acetylcholine. There's just the release of acetylcholine, but the receptors are there. So you have to have this kind of a receptor setup, the neurotransmitter being released, and then downstream we have the receptor. In most cases, it works that way. There are some exceptions to that, which we'll kind of talk about later on. All right, so what does it mean here? What we're trying to work towards is understanding the drugs and how the drugs ultimately alter synapse function. So basically, remember, we know this already. We've talked about this. So drugs can do one of two things. They can stimulate or they can block receptors. So the synapse is a super important target for drug action. The synapse and the end of the postganglionic neuron and the target, that's the big one actually. The synapse gets a little bit messy. The ganglia gets a little bit messy. But if we want drugs that will stimulate receptors, there's different ways that drugs can be formulated to kind of modulate this response. One is we can make a drug that acts just like the neurotransmitter, and it hits this receptor. So that would be called a receptor agonist. So if it's a cholinergic receptor that we're looking at, let's say a muscarinic receptor at the target, we haven't talked about that yet, but that's the second type of cholinergic receptor that binds, it's cholinergic, so it binds acetylcholine. So if we formulate a drug that looks just like acetylcholine and it fits into that receptor at the target, that would be a receptor agonist, right? So that's one option. Another thing is we can design a drug that causes us to release more acetylcholine or norepinephrine, depending on the scenario. That would stimulate, that would cause a stimulatory action, right? That would, if it was a norepinephrine increase, it would cause an adrenergic response, fight or flight looking stuff. If it was acetylcholine and a muscarinic receptor, it would cause what would be that restorative sort of state, depending. The other option we can do is we can, if we're trying to stimulate, if we're trying to have a stimulatory action, either fight or flight in the case of the sympathetic nervous system, or rest and digest in the case of the parasympathetic nervous system. So if we're trying to potentiate that action, the third option is to block the mechanism that gets the neurotransmitter out of there. Right? If you block the acetylcholinesterase enzyme, then the acetylcholinesterase that's in the synapse is going to keep hitting that receptor and hitting the receptor and hitting the receptor. Every time it hits, we see an action, right? So by blocking the removal of the neurotransmitter from the synapse, it acts as if it lends itself to stimulation. Does that make sense to you guys? I hope that makes sense to you. The flip side of this would be if we wanted to inhibit the action at the receptor. So to do that, we could make a drug that parks on the receptor, right? That would be a standard receptor antagonist, right? That's easy to understand. I think we would just block the receptor. Nothing can get on there. The other option is to block the release of neurotransmitter. So if we give a drug that makes it so we don't release the neurotransmitter, then you're not going to get as much neurotransmitter into the synaptic cleft, and you're not going to get any stimulation, and instead you would see inhibition or lack of stimulation. It kind of depends on the scenario. But those are sort of the general ways that drugs are going to alter synapse function. Of course, we're going to, look at a lot more detail at this as we go. But here's a visual, sort of just summarizing what I just told you. So here are the agonists over here. Here are the antagonist actions over here. And again, these are the things I just mentioned, right? the drug increasing the synthesis of the neurotransmitter molecules, so you make more. Usually you do that by giving more substrate, giving more precursors. You can increase the number of molecules by destroying the degrading enzymes. I just talked about that. You know, you can do all kinds of stuff, right? There's all sorts of things. This autoreceptor business, I'm going to talk more about in the central nervous system section, so don't worry about that right now. It just adds another level of complexity that we don't need to get. But anyway, you can look at this slide, review it at your leisure, and it just gives us a visual and just sort of another way to kind of think about how drugs, because that's where we're ultimately going, how drugs can alter synapse function. Okay, so I hope that made some sense to you. Spend a little bit of time making sure you get this, and then we're going to next move into more specific cholinergic first, and then adrenergic responses second.